All right, this is on periodic table trends. What you see in the picture right now is similar to what your graph is going to look like, except this is a bar graph. I want yours to be a line graph. But the thing is, across the bottom are, say, the first 50 or so elements, not like they are in the periodic table where, every 8 or so it circles back around and starts a new row. These are all in one long row. And the whole reason it's called periodic is you can see it goes up and down and up and down. And in fact, all those high points on this graph are all in the same column, the same group of elements. This is a picture of atomic radii, the radius of the atom, or how big the atom is. You can see a couple of the numbers at the bottom, 3, 11, 19, 37, 55. Those represent the atoms in column 1, the alkali metals. Those are the high points on this graph. And then they go down from there. So, for example, number 3, which on your periodic table would be lithium, we are then moving across row 2. And then we jump up here, here's sodium, and then we're moving across row 3. And then up here, now we are to potassium and moving across row 4. And if you're like, hey, row 4 and row 5 are much bigger than rows 2 and 3, well, right in here is where we've brought in the transition elements. So if you are to graph all the atomic radii, you get this periodic nature, up and down, up and down. And it so occurs that the periodic table is set up so that all these peaks end up in the same group. So, atomic size, first thing for you to write down. What you need to understand about this unit, or this portion of the unit, is you need to know by heart the trends. And by trend, I mean the pattern of what this particular subject does. For atomic size, or the radius of the atom, as I go across the table, the atoms get smaller. As I go down any particular column, the atoms get bigger. Now, why does this happen? Well, as I'm going down, I'm adding shells. And each new shell adds outside of all the ones that occurred before it. So when we have lithium with 2 shells, and then we move down to sodium, it now has 3 shells. That third shell is outside of the other 2. And so it's a bigger atom. And then I move down to potassium, and it now has 4 shells. Why do they decrease as they go across? After all, I'm adding protons and neutrons and electrons as they go across. Why do they get smaller? Well, they get smaller because all the protons that are being added are all being added in the same spot, the nucleus. And as a result, the nucleus gets stronger and stronger as I move across a particular row. And the stronger it gets, the tighter it pulls in all of those energy shells. As I said before, the kind of question you would get on a test or quiz would be like, I'd give you 4 elements and I'd say, hey, which one of these is the biggest or has the biggest atomic size? Which one of these has the smallest? Well, if the 4 of them are all in the same period, all in the same row, then our trend says they get smaller as they go across. So the biggest one would be to the left. The smallest one would be to the right. If the 4 elements are all in the same group, say the alkaline earth metals, which are in column 2, well, this says increases as it goes down. So the biggest ones would be towards the bottom of the column. The smallest ones would be towards the top. So that's what you need to know, is how does the pattern work and what the Y is. But you don't have to worry about what any of the actual numbers are. You would not be tested on what's the atomic size for any particular atom, just how do they change in general. Okay, ionic size. In other words, how big are the ions? Now, as a general rule, the ions follow the same pattern as the atoms do. In other words, they get smaller as they go across, and they get bigger as they go down for the same reasons. However, there is a little hiccup in this pattern. First off, remember we have two kinds of ions. We have the positively charged ions called cations, and we have the negatively charged ions called anions. The cations, positive, have lost electrons. These are usually the metals. So these are, for the most part, the ones on the left side of the periodic table. The anions, the negatively charged ones, those are atoms that have gained electrons. These are usually the nonmetals, more in the upper right corner. Here's the thing though, when a positively charged ion that has lost electrons, when we look at its size, it's a little bit smaller than the original atom. It lost some electrons. It still has the same number of protons, and so they pull the shells in a little more tightly. It's a little bit smaller. For the negatively charged ions, they gained electrons. They got to have space to put those extra electrons in. They're actually a little bit bigger than the original atoms. Well, here's what's happening in the table. As I go across, when I get to that staircase part of the table, that black line that kind of zigzags across the table, I switch from being positive ions to being negative ions, which means I go from being a little bit smaller to a little bit bigger than the original atoms. So there's a jump in size. Now, after I go past the jump, the trend holds. In other words, as I move to the right, they still decrease. But it is important to know that the positive ions are a little smaller, the negative ions are a little bit bigger, and that there's going to be a jump as I move across near that staircase when I switch from the positive ions, which have lost electrons, to the negative ions, which have gained electrons. Okay, ionization energy. This is the trend for ionization energy, and the first thing I'd like you to notice with the numbers that are down there at the bottom is now the 3, 11, 19, and 37, the alkali metals, they're the low. And the high, which is just one before the 3 and 11, 19, well, those happen to be the noble gases. So ionization has an opposite trend compared to atomic size. Well, what is ionization energy? Ionization energy is the energy needed to remove an electron from an atom. When an atom loses electrons, it doesn't happen just automatically. There is some energy required. And it turns out that the amount required varies as I go across. I need more energy to take away an electron as I go across. I do not need more energy. I need less energy to remove an electron as I go down one particular column. Why? Well, as I go across, the shell is becoming more and more full. And in fact, when I get to the noble gases, my shell is completely full. It does not want to lose any electrons. It's most stable being full. And so it's going to require a lot of energy to remove that one electron. On the other hand, all the way over at the other side, the left side of the table, where I have the alkali metals, well, they only had one valence electron in that last shell. They kind of want to get rid of that one electron so that they go back to being like a noble gas. So it doesn't require very much energy to get rid of one, as opposed to gaining 7 more. And so it sets up, we have increasing energy as we go across. Now, why does it take less to go down? Well, remember, we're adding shells. And as we add shells, those valence electrons get further and further away from the nucleus. So they don't feel the nucleus's pull quite as strongly. So as a result, it doesn't take quite as much energy to remove a valence electron that's in the 5th shell as it would in the 3rd shell. Now again, what you have to know, besides the whys, is if you were given 4 elements in a row, hey, which one would require the most energy or which one would require the least energy to lose an electron? Or maybe the 4 elements would all be in the same column. Well, according to our trend, the ones near the top of the table would require less energy than the ones towards the bottom. Notice it decreases, so you're going to need more energy on the bottom than on the top. Notice that the Ys are pretty much the same Ys. The shells are becoming more full as we go across. We're adding shells as we go down. It's just the effect is a little bit different. For this, I'm getting further away, so it feels the nucleus less. On the other hand, because it's further away, the atom is bigger. Okay, we have another trend called electronegativity. I'm going to flash back for a moment to ionization. There's the ionization one. And here's the electronegativity. What's the first thing that stands out? Yeah, there are gaps in the trend. And if you note the numbers of those gaps, which are right before the 3, 11, 19, and 37, those are again the noble gases. Well, electronegativity is about losing electrons. Electronegativity is about gaining electrons. Ionization was about losing them. So as a result, noble gases, they don't want to lose anything. They don't want to gain anything. They're full. They're complete. They don't want to do anything at all except just sit there. So there are no electronegativity values. They're not zero. There just aren't any for the noble gases, which makes the high points one column before the noble gases. These are the halogens. Otherwise, they pretty much do the same thing. So electronegativity, which is also called electron affinity, it is the degree to which an atom wants to gain another electron. And as I mentioned, noble gases are already full, so they're not included. They don't want to gain anything extra. However, those halogens right next door, so that one would be fluorine, for example, they only need one more to get full. The halogens really want that one extra electron so that they would be like a noble gas and be full. Over on the left side, however, you've got the alkali metals, and adding one more does make it a little bit more full and actually does fill in some space that's useful, but as a rule, doesn't really want one more as much as the halogens do. Likewise, as we go down a column, we're adding shells. We're getting further from the nucleus. So the amount that the atom wants one more electron is also decreasing because the effects of that outermost shell are not felt as strongly as the ones that were closer in. So increases as I go across, decreases as I go down the periodic table. Electrons are farther away from the nucleus is the reason it decreases as you go down a column. electrons are farther away from the nucleus. Now, density really is kind of different from all the ones we've looked at so far. Density is the biggest, not on the left side or the right side, but in the middle. And really, this is because of the nature of the atoms themselves. These guys over here on the left are metals. These guys over here are nonmetals. Not only nonmetals, they're gases. Gases do not have the same density as solids. They have a much lower density. So the biggest area density-wise is right here in the middle, near where you have things like gold, for example. Okay? Now, it does increase as I go down. So, gold is more dense than silver, which is more dense than copper. They're all in the same column of the transition metals. So it's the lower you go, the more dense it is. Likewise, even when you look at, say, the halogens, you find that fluorine and chlorine, bromine, they're all gases, and then iodine often is in liquid form, and then acetylene is in a solid form. So they are, again, getting more dense as I go down. So this one's a little different because of the nature of being metals over here and nonmetals over there. Okay, now this might not even seem like a trend because it's like, duh, yeah, the masses always get bigger. Every time I go anywhere, they get bigger. I'm adding protons, I'm adding neutrons, I'm adding electrons. So of course it increases as I go across. And I'm adding shells, so of course it increases as I go down. Here's the funny thing though. There are two spots on the table, cobalt to nickel and tellurium to iodine, in which the mass on the periodic table actually goes down. Even though I've added more protons, remember when I move over one, I've added a proton. Even though I added a proton and probably have added neutrons, the mass on the periodic table has gone down. Well, that has to do with the fact that those masses are actually averages of the isotopes. What's an isotope? Different forms of the same atom with different number of neutrons. And so while on average, nickel might have, say 30 neutrons, well, some of the isotopes might only have 29 and some of them might have 31. And it's that averaging kind of thing that leads to an average for nickel being a little bit smaller than the average for cobalt. Most of the time, things just go up as they go across, mass-wise. Most of the time, they just get bigger as they go down. But there are these two exceptions to the rule. Now, this chart is also in your book towards the end of chapter 6. It kind of summarizes all the trends that we've been talking about. Now, the one downside is the arrows only point toward getting bigger, increasing. Generally speaking, questions that I would ask you are going to be either going across from left to right or going to be going down a column. So understand that if you're going opposite the direction of the arrow in this chart, it's getting smaller. So atomic radius, biggest on the left, biggest on the bottom. Ionization and electronegativity, biggest on the right, biggest on the top. So that's the way to read this. This would be a really good table to write down as a summary of all the different trends. And then as a reminder from our last set of notes, we already had a couple of trends. We had one for valence electrons. Remember I said, I don't want you thinking about there's 2 in the first shell and 8 in the second shell and so forth. You're only going to be asked questions for those 8 columns because there's a nice pattern for them. Everybody in the first column has 1 valence electron. Everybody in column 2 has 2. Skip the transition metals. Everybody in boron's column has 3 valence electrons. 4, 5, 6. Halogens all have 7. Noble gases all have 8, with the exception of helium because it only has 1 shell and therefore it can only contain 2 electrons. And then we had a trend for the ion charge. All the alkali metals in column 1 make a +1 charge. All the halogens in column 17 make a -1 charge. And of course, noble gases don't make ions, so they are 0. So this completes our notes.